This semester, our team partnered with the Clemson IEEE robotics team to develop a robot for the SoutheastCon 2021 hardware competition. This is an annual competition between schools in the Southeast region. The challenge for this year's competition was loosely based on the Pac-Man arcade game. In this spin-off, a robot must navigate from the starting location to either corner A or corner C at the top left and right, where a power pellet block is located. It must also avoid two ghost blocks positioned randomly in the spaces marked G1 through G5. Once the robot secures the power pellet, it can go back and hit the ghost blocks to quote eat them and earn further points. Two purple blocks marked with a triangle and circle represented a power pellet and poison pellet. Similarly, two red blocks marked with a triangle and circle represented the two ghosts. After securing the pellet, the robot must eat the ghosts with the shape matching the power pellet first.
Our primary objectives included using physical devices like a rotary encoder and switches to specify the location of the pellet and ghost blocks on the board, using audio to communicate which pellet is the power pellet, moving to the approximate location of the power pellet without hitting ghost blocks and trying to avoid the walls, using a computer vision system to identify the exact location of the power pellet and communicating with the navigation system to align the robot with the pellet, and using an adhesive plate mounted on a 3D printed arm to pick up the pellet and leveraging the vision system again to confirm we picked it up successfully. If we failed to pick up the pellet, we would try 2 more times to pick it up, and then, assuming we were able to get it, we would move to hit the ghost blocks, ensuring we first hit the one with the shape matching the power pellet.
There are 4 primary subsystems on our robot. The first is the startup subsystem, circled here in red. This consists of a rotary encoder and switches used to indicate the positions of the pellet and ghost blocks on the board, as well as a microphone and start button. This view also shows the arm with its adhesive plate that is attached to a servo motor and used to pick up the power pellet.
Mechanism wheels are used on our robot that theoretically allow for movement in any direction. Distance sensors are also mounted on each side of the robot to measure the distance between the robot and nearby walls. Once the robot reaches the approximate location of the power pellet, a computer vision system run by a Raspberry Pi 0W and a PiCam is used to pinpoint the pellet's precise location.
Our system was powered by a 3000 mAh battery with a 5V and 12V output. This diagram shows how we leveraged the 5V output to power our control units, namely the Teensy and Raspberry Pi, and how we used the 12V output to power the servo and stepper motors. You can also observe 3 switches that can be used to cut power to the different components in case of emergency.
On the physical robot, the switches circled in green and blue are the E-stops for the stepper and servo motors that control the wheels and acquisition arm, respectively. The switch circled in red could be used to restart the Teensy and reset the game state. Finally, you can see our battery positioned in front of the robot and its rectangular slot marked in yellow. Now, let's take a look at a full run in action.
The user will first use the encoder and switches to enter where the pellet and ghost blocks are. The top 2 switches are used to indicate whether the 2 pellet blocks are on their wider or thinner face. This distinction is used in the vision system to adjust the thresholds for identifying the block. The third switch is the E-stop that controls the power to the acquisition arm. When inputting a number, the 100 place denotes the position of the pellet, marked with a circle, 0 for when it's located in corner A, and 1 when it's located in corner C. The 10s in 1 place indicate the position of the ghosts, marked with a circle and triangle, respectively. They could be in one of the 5 positions outlined earlier. After the user has finished this input stage, there's a 30-second period in which the proctor will announce which of the 2 purple pellet blocks is the power pellet by indicating whether the power pellet is in the corner A or C, and the user relays this information to the robot using audio communication. In our system, the user would yell if the pellet marked with the triangle is the power pellet and remain silent otherwise.
The pellet is in corner A.
As the robot prepares to move, its display reflects the location of the power and poison pellets using 0 and 1 to denote corners A and C, as well as the location of the ghosts corresponding to the power pellets with values 0 to 4.
At this point, the robot has all the information it needs to get to the power pellet's approximate location and navigates there while avoiding the ghosts. As it approaches the corner, notice how it starts to shake a little bit. This is caused by the robot reading from the distance sensor mounted on the front. We found that each read of a distance sensor takes about 40 milliseconds, which is a long time relative to the speed that the Teensy needs to drive the stepper motors otherwise. This delay prevents the stepper motors from spinning in a continuous motion. While we had originally intended to use the distance sensors to make each movement more precise, this became unrealistic combined with the fact that the sensors were only accurate out to about 35 centimeters, even though they were advertised for accuracy out to 1 meter. Ultimately, we only ended up using the distance sensors in a few key locations. Given the relatively small number of cases for the game board configuration, we created cases for each combination of the pellet and ghost block placements. These cases were used to hard code in distances and directions to travel to reach the pellet's location from the starting location. When traveling across the longer dimension of the board, we observed the robot would sometimes run into a wall if it was not moving perfectly straight. To mitigate this, we checked the robot's distance to the wall at a preset point as shown here, and move laterally left or right by a small amount to recenter the robot if needed.
The vision system running on the Pi uses two masks to line up the robot with the block. The first mask is strict to mitigate all noise from the HSV image to determine whether a purple block is in the frame. Once it recognizes a block, a less strict second mask is applied to the original image to determine the contour of the block. Once the purple block is identified, the midpoint of the contour is compared to threshold values to determine when the robot's arm is lined up with the block. Throughout this process, the Pi is communicating with the Teensy to tell the Teensy when to move and in which direction to line up with the block. Once the Pi verifies the robot is aligned, the arm is swung in an attempt to retrieve the block. After the arm is swung, you'll notice a pause as the Pi checks for the presence of a purple block. If it's still there, indicating the pickup failed, the arm can be swung up to 2 additional times to try to retrieve it.
Initially, we were concerned about the consistency of picking up the block, as we had difficulties finding a good adhesive. After we discovered carpet tape, this actually became one of the most consistent parts of the project, and we were able to pick up blocks even with only 2 to 3 square inches of contact.
Assuming the power pellet pickup is successful, the robot will move to hit the ghost, ensuring that it first hits the ghost with the shape matching the power pellet. Here, you can observe again the use of the distance sensor, as we had to make sure the robot was perfectly aligned to fit through the small gap in the middle of the board.
Our biggest challenge throughout the project was the consistency of the movement. By using the mechanism wheels, we had hoped to be able to move laterally with ease and avoid any 90-degree turns. We quickly found that this lateral movement was not nearly accurate enough to be useful for our project, so we had to revert to moving primarily in the forwards-backwards direction, although small lateral moves were still used when recentering the robot as mentioned earlier and when realigning the robot to pick up the power pellet.
Adding a covering over the wheels also helped mitigate inaccuracies in the movement. This helped if the robot were to glance a wall with a wheel. Instead of the wheel getting stuck driving into the wall, the cover would keep the wheel from making direct contact with the wall and allow the other 3 wheels to correct the robot's course.
Aside from the navigation, all of the subsystems consistently performed as designed, and we were happy with the overall result achieved in approximately 10 weeks that allowed us to win first place by a wide margin at the regional IEEE competition.
We'd like to thank Jacob Thompson, Nolan Howard, and the Clemson IEEE robotics team for allowing us to work with them this semester, and Matt Leckenbush for serving as our proctor for the competition. And lastly, the Clemson ECE department who provided funding for the project. And thank you for watching this video.